Alicia, and I'm with Chariot Solutions. I'm here to introduce our speaker, Adam Tornhill, talking about prioritizing tech debt, an internal problem that I try to solve in my job. So looking forward to hear what you have to say about that. Take it away, Adam.
Thank you very much for the introduction, and hello everyone, and welcome to this session on prioritizing technical debt as if time and money matters. So this is a pretty broad topic, so let's start by jumping right in and have a look at the forces that we always need to balance when building large-scale software systems. And I do think that these forces are very well captured in something known as Lehman's laws of software evolution. So there are multiple laws of software evolution, but what I want to do today is to just present you with the two I think are the most important. And then let's see if they resonate with your experience. So the first law of software evolution is the law of continuing change. And the idea here is that the system has to continuously adapt and evolve, or it will become progressively less useful over time. Is this something you recognize? Yeah, I think so, right? This is the very reason why we keep adding new stuff, why we keep adding new features to existing products, because a successful system is never done. But what I want you to do now is to notice that there is some kind of tension to the second law of software evolution, and that is the law of increasing complexity. And this law claims that when a system evolves, its complexity will increase unless we actively try to reduce it. And this is interesting, isn't it? On one hand, we have to continuously adapt and evolve and build out our systems. But when we do, their complexity will increase, right? Which in turn makes it harder and harder to respond to change. So this is a vicious circle that we need to stay on top of. And when we fail to do that, the main problem I have seen is that what we tend to experience then are symptoms rather than the real root cause of increasing complexity. And to make it even more challenging, the symptoms that we're going to experience are different depending on who we are, depending on what our role is, right? So if we work on the development side, what we tend to see is that we tend to experience long lead times, right? So what used to take 2 days suddenly take 2 weeks or maybe even 2 months, right? It takes longer and longer to implement a new feature. And as a consequence of that, we tend to get a very low predictability. It becomes even harder to guess when something will be done. So this is the product side of things. What our end users tend to experience is this. They tend to experience an impact on the external quality of our code. They tend to experience bugs, while the real root cause tends to remain hidden, opaque, and obscured. So if increasing complexity and growing technical debt is such an important topic, why don't we try to bring visibility to it? There have been several attempts over the year, and I would like to start with something that I experienced firsthand a couple of years ago. And that was an attempt to quantify technical debt. So the idea here is that what if we could put a number on the amount of technical debt that we have? Dollars, hours, some kind of currency, right? And the first time I saw this was like maybe 5-6 years ago. So back in those days, I used to do some consulting. So I went to different clients and I analyzed the code and I tried to come up with recommendations on how do you prioritize your technical debt? Where do you pay it down? And one of the first clients I visited had done something pretty interesting prior to my arrival. They had used a static analysis tool capable of quantifying technical debt. So they had basically taken this tool and thrown it at their 15-year-old code base. And this tool reported that on your 15-year-old code base, you have accumulated 4,000 years of technical debt. I like to put things into perspective. So 4,000 years ago, that was here. That's the start of recorded history for the invention of writing. And I mean, of course, we can always question what kind of programming language did they use 4,000 years ago, right? Was it a Lisp? Was it a Fortran? But on a more serious note, I want to point out that 4,000 years of technical debt, it might very well be accurate. I mean, who could tell, right? And the reason for that is because on a 50-year-old code base, they had hundreds of developers working on it in parallel. So that potential debt could have accumulated very quickly. So it might be accurate. It's definitely depressing, but how useful is that data? Is it actionable? Not really. There's simply too much information here. 4,000 years of technical debt. There's no way we can act upon that. And this is where it starts to get dangerous when we attempt to quantify technical debt. So let me tell you what I mean about that. Since back then, I have come across the same situation multiple times. Organizations try to analyze the code. They try to come up and identify all cases of technical debt. And when you do that on an existing code base, it's going to be a long list. So I've heard organizations say things like, all right, so we have 7,000 major issues. What we're going to do now is that we're going to invest a month or 3 months into bringing that down to just 5,000 major issues. That should improve things for sure. And when I hear that, I always advise against it. Because to me, going from 7,000 issues down to 5,000, it's a little bit, like jumping from the 5th instead of the 7th floor. Most likely none of them are a good idea. And the reason I say this is because we need to consider what kind of behavior that we reinforce by attempting to putting a quantitative goal on technical debt. Because what's very likely to happen is that we're going to make our best that we actually meet that goal. And we're going to do it by picking tasks that we are most comfortable with, that we are familiar with. Because what's always missing in a quantitative goal like that is the most important factor, and that is the business impact. And the business impact is simply something that we cannot read out of the code. So to sum up what I've told you so far, I want to point out that quantifying technical debt simply isn't actionable. More important, technical debt just cannot be prioritized from the code. Technical debt is invisible in the code. What we might be able to read out from the code is the cost to rework, right? The remediation cost. But the cost of technical debt is something very, very different. It's the additional cost of implementing something new, right? It's the additional cost of fixing a bug. It's that overhead, and it's just not visible in the source code. At the same time, it's still important, right? Because we always have this trade-off, right? Between improving existing code versus adding new features. Remember Lehman's law, the laws of software evolution. And this is a balance that's going to shift over time. So what that means is that we do need a way to identify and prioritize technical debt. But how can we do it if it's not visible in the code? Well, those of you who might have read one of my books, or maybe even attended one of my previous sessions, you know that I'm a big fan of version control data. So I guess we all have our odd hobbies, and version control data happens to be mine. And the main reasons I'm so fascinated with version control data is because version control is something that we have been using for decades. And most of the time, we have been using version control as an overly complicated backup system and occasionally as a collaboration tool. But in doing so, we have built up this absolutely wonderful data source, a data source over how we, as developers, have interacted with the code that we're building. And this is a data source that we can tap into to prioritize technical debt. Let's make this real by looking at a real-world code base. And for my first case study, I want to pick a code base that I think some of you might actually have laying around on your desk or carrying around in your pocket as I speak. Because I'm talking about this. I'm talking about Android. More specifically, I want us to look at the part of Android known as the platform framework base. The platform framework base, it's a large code base, right? 3 million lines of code, most of it written in Java by thousands of developers. And the visualization you see here is something I call a hotspot analysis. The actual visualization style is called enclosure diagrams that I tailored a little bit. So let me walk you through a hotspot analysis so that you know what you see. First of all, if you look at the circles, the ones that blink on screen right now, Each one of those circles corresponds to a top-level folder in the Android repository. So if this was your code base, you would recognize the names of those folders as important subsystems or top-level components. It's also entirely hierarchical and interactive, so I can zoom in to any level of detail that I'm interested in, then see other subfolders. And once I get to the lowest level of detail, I see that each file with source code is visualized as a circle. And you see that those circles, they have different size, right? That's because size is used to represent code complexity. How hard is that code for a human to understand? And I'm going to talk much, much more about code complexity soon. For now, I just want to point out that this is actually the least interesting dimension. And the reason I say this is because just because some code is complicated, that doesn't mean it's a problem. It's only a problem when we need to deal with it. So when we find some complex code, we basically need to figure out, is this code that actually has an impact on us as a developer organization? Is this code that might impact the business? And this is actually data that we can pull out of a version control system. So I go to version control and I simply look at how many changes, how many commits have we done to each piece of code, and I sum it up, and I use color to reflect the change frequency. And when we combine these two dimensions, we can identify complicated code that we have to work with often. And that's our hotspots. Now, we're going to return to Android, and we're going to return to this hotspot that you see on screen, the ActivityManager service, in just a minute. But before I do that, I promise to talk a bit about code complexity. Because it turns out complexity in itself is really, really complicated. In particular, I personally dislike the term code quality. And the reason I dislike it is because I just don't think there's any such thing. And code quality kind of suggests an absolute, whereas the reality is much, much more complicated and contextual. And this is something that's actually supported by some research. So let me show you an extract from one of my favorite research papers. So it's a pretty old paper, but it's still very, very valid. And what this paper claims is basically that we're doomed if we start to look for a single number to capture a multifaceted concept like code quality. There is just no such thing, right? Instead, what I have been doing over the years is I've been experimenting with lots of different proxies for code complexity. And then what I ended up doing was taking a lot of inspiration out of this paper, in particular the second paragraph here, that claims that the most promising approach for code complexity is to identify specific attributes of complexity, and then we measure these separately. So that's what I tend to use when I investigate hotspots. And I kind of call that aggregated technique code health. So when I find a hotspot, the first thing I want to figure out is, all right, it's a hotspot. That means it's relevant because we work with it all the time. So any technical depth here might have a high interest. Then I start to look for symptoms of low code health. And the factors that I tend to pick are ones that are known from research to correlate with increased maintenance costs and increased risk for defects. So just to give you some examples, I start to look for things like low cohesion. This hotspot that we have here, ActivityManager service, is it really just doing one thing, or does it implement multiple different features? I start to look at the deeply nested logic. So deeply nested logic is interesting. It's basically the case when you have if statements, it's an if statements, it's an if statements, and then maybe a loop at the end, right? And the reason those constructs are interesting is because there's some pretty good research that suggests that roughly 20% of all programming mistakes are due to constructs like deeply nested logic. And they're also pretty easy to avoid once we know about it, right? So I continue like that. I look for all these different symptoms. And let me give you a spoiler here without looking at the code. If we look at the ActivityManager service, the hotspot in Android, we see that it actually ticks all of these boxes and some more. And this is interesting because it means that not only have we found a complicated piece of code, it's also a development hotspot. So this is actually technical depth that impacts us. But maybe maybe we're doing so much work in the Activity Manager service because we are already aware of these issues, and right now we're refactoring it. So maybe that's the reason why it's being a hotspot. This is a question that we can actually answer by turning back to version control data. So what I do is when I find a hotspot, I go to version control, and then I pull out each historic revision of that code. And I measure the code complexity over time, and I plot a trend like this. So if you look at this graph, you see that the blue line is just the accumulation of lines of code. And we see that this hotspot has been growing and growing and growing over time, right? An accumulation of code might actually be a problem itself. But I'm more concerned when I see the red line, which is a proxy for complexity. So what I do here is I measure the nesting depth, the shape of the code, and I plot that over time. And we see that the red line, it increases at a much steeper rate. So this kind of indicates that we have a growing problem here. Now, what I tend to do is I use these graphs and these findings to communicate within the organization so that everyone has a shared understanding of where the worst problems are. And I also like to emphasize that finding a hotspot with the code health issues, it's not just about the financial perspective. It's not only about being more efficient, about being able to implement things quicker. It also has a security impact. And there is some very recent research that started to look at code health factors and how they correlate with security errors. And this was studied on a bunch of open source iOS operating systems. And what researchers basically found out that low code health does lead to a high number of total security errors. And even more interesting was that to find a correlation between security error density and hotspots. So hotspots kind of tend to be defect magnets. Now, with this covered, it's clear that if we want to improve things here, we have found a first candidate where we can dig deeper. The question is, of course, how do we act upon this? Because looking deeper at the data, we see that Activity Manager service, it's a hotspot with 20,000 lines of code. Who would like to have that refactoring task? Hopefully no one, because my take is that we should never, ever take on a refactoring at that scale. It's simply going to be a huge risk, in particular when we consider that 74 developers have contributed to that hotspot just over the past 3 months. So what that basically means is that if we branch out and start to refactor the Activity Manager service, we will never, ever be able to merge it back, right? So what I do instead when I come across a large hotspot is that I use another behavioral code analysis technique that I call X-ray. So here's how that works. I basically take that hotspot and I parse it into different function blocks. And then I look at the Git log, where do each commit hit over time? And I sum that up. And that basically gives me hotspots at the function level. And this is what I use as a starting point for refactorings. Let's have a look at the data from Activity Manager service. So what we see here with X-ray technique is that the number one hotspot at a function level is a function called handle message. And we can see that the change frequency column tells us that just over the past year, there have been 98 commits that modified handle message. So like twice a week, some developers impacted by the excess complexity in that method. And we can kind of get a very rough estimate on the complexity by looking at the final column that says cyclomatic complexity. So cyclomatic complexity is one of these really old complexity metrics from the 70s. And what it does is basically calculating the number of branches through that function. So each time an if statement +1, each time you have a loop +1, and so on. And the only reason I use cyclomatic complexity is because cyclomatic complexity is a pretty good estimate on the number of unit tests I would need just to cover that method. So it kind of communicates something about the complexity, doesn't it? We also see from the column in the middle that the number of lines of code in handle message is 500. 500 lines of code for a single method. That's quite a lot, isn't it? It is. But 500 lines of code is much, much less than 20,000 lines of code, which was sized with a total of 5. And 500 lines of code is definitely less than 3 million lines of code, which was the size of total code base. So more important, we are now at the level where we can act upon this data and do a focused refactoring based on how we, as an organization, actually work with the code. All right, with that covered, I would like to explain why Hotspots work so well to prioritize technical debt. So please have a look at the following graphs. They might be the most important I'm going to show you today. So what you see here is data from 3 different code bases, and they all show the same kind of data, right? On the x-axis, we have each file in the system, and those files are sorted according to the change frequencies, the number of commits, which what we'd see on the y-axis. And if you look at the top row, you see that I've picked examples from 3 radically different code bases. So those 3 code bases, they differ in all kinds of aspects, right? They're implemented in different programming languages. They target different domains. They're implemented by different developers, different organizations, different lifetime spans. Everything is different. And yet, they all show exactly the same pattern. They all show a power law distribution. And this is something I've found in every single code base that I've analyzed so far. And I've probably analyzed around 300 code bases by now. So this seems to be a very stable rule. This seems to be the way software evolves. And this is important for us. This is good news, because what it means is that most of our code is likely to be in the long tail. So it's code that's rarely, if ever, touched. So those are the parts of the code where we can actually live with some technical debt without it being that expensive. What our hotspots do is to identify the parts of the code where most of the work is. And that's the part of the code where even a minor amount of technical debt can quickly become really, really expensive due to the high amount of development activity. But there's more to it. So in my latest book, I have a chapter that I called Your Best Bug Fix is Time. And what I did in that chapter was basically that I summarized some research that had looked at how aging impacts correctness. And what the researchers found was that code that hasn't been modified for a year was much more likely to be bug-free than code that we've worked on recently. And that was independent of how large our recent changes were, right? It turns out that modifying code is one of the most risky things we can do. Who knew? But this is interesting because we need to consider, why does code grow stable? Why do we stop changing a piece of code? Why does it drift off into the long tail of a polar curve? Well, there are 2 primary reasons that I've seen. The first is my favorite, and that's simply because it's dead code, right? It's code that's not even used, right? Maybe no one is even calling that code. And it's my favorite code because dead code can simply be deleted, and less code is always better. But then there's other type of code. It might not be perfect. It might have some code quality issues, right? But maybe it has been debugged into functionality. It just works wonderfully in production. It just does its job. And having code of that quality is also quite nice. So what hotspots help us with as well is to draw that separation between the stable parts of the code that are likely to be correct and the more volatile parts. And this is something I've been using when working with testers, so that we can get the most out of our efforts by focusing on the volatile parts that are likely to contain more bugs. All right, I want to show you one more thing before I leave time for questions. Because when talking about technical debt, it's almost impossible not to mention legacy code. Because the 2 concepts, they are related, but they are not the same. There's a distinction between technical debt and legacy code. And I like to try to clarify that. So what is legacy code? Well, I'm afraid that there are as many definitions as there are conference speakers. And of course, I have my own definition too. So to me, legacy code is something that's typically used to describe code that, first of all, lacks in quality, and more important, code that we didn't write ourselves. And the second part is important here. that we didn't write that code ourselves. So let me share a story with you. So this is something that happened to me a couple of years ago. So I regularly run workshops around these topics, right? And I was visiting an organization, and we spent some time analyzing their two code bases. So we looked at the hotspots, we inspected the different code issues that we came across. And what we pretty soon found was that both of those code bases, they looked rather healthy. You picked up the hotspots, and yeah, there were always some minor improvements that you can do, but overall there wasn't any big concern. So this looked pretty good. But then one of the team members told me that, you know what, we actually have a third code base as well. And I said, yeah, but let's do a hotspot analysis of code base number 3 as well. And everyone kind of looked at each other and said that, yeah, you know, we could do that, but you know, we know what we will find. We know for sure that code base 3 is going to be a mess. It's impossible to understand. So I thought, even more fascinating, now it's really time for a hotspot analysis. So we picked up code base number 3. And guess what? By looking at the results of the hotspots, we could see that there was no objective difference in terms of code complexity or code quality between the first 2 code bases and the third code base. They were equally good. And this was fascinating, because why was that impression there that code base 3 was so messy and so hard to understand? When I dug a little bit deeper, I found out that code base number 3 was actually developed by a different part of the organization, by a different team in a different part of the world. And that team had since been disbanded. And this team had simply inherited that code. So the reason this code was perceived as hard to understand had more to do with unfamiliarity with both the problem and the solution domain. And this kind of made me think, because if it's that easy to create legacy code, how quickly can we take a current code base and turn it into legacy code? Is there such a thing as a legacy code making machine? Well, let's see. And this time I want to look at a different code base. So we looked at the Java code base. So let's pick up a C# code base now. This is ASP.NET MVC Core from Microsoft. It's a framework for building dynamic web applications. And it's a mid-sized code base, so roughly 350,000 lines of code. But like most popular open source projects, there are lots of contributors. So there have been roughly 180 contributors to ASP.NET MVC Core at the time of the analysis. Now, if we look at this from the legacy code perspective, it's easy to think that you're safe with 180 contributors. You know, if 1 or 2 are going to leave, that's probably not going to make a big difference, right? Well, nothing could actually be further from the truth. And the reason for that is because power laws are everywhere in software evolution. So let's look at a different data set here. Let's look at the contributions sorted by the number of authors. We see exactly the same distribution as we saw when it came to change frequency. Some authors, some contributors have simply contributed so much more code. And these might be the people that are employed at Microsoft and working full time on this code base, right? So what would happen if we lost one of those top contributors? What if we pull them out, we put them on another product, or they might even leave the company? What's the impact of that? Using behavioral code analysis, you can actually get a pretty good view of that. And in order to get that view, we need to look at a different data point. We need to look at the social side of code. And again, why I'm so fascinated with version control is because it's actually social data as well. Because our version control system knows exactly which developer that wrote which piece of code and when they did it. So this is data that we can simply aggregate together and reason about the impact if a developer leaves. So let's return to ASP.NET MVC Core and see how it looks. So what I did here, so this is the same visualization as you saw before, the same style as we used for hotspots, only now the colors carry a different meaning. Because what I did now was that I aggregated individual contributors into 2 different groups. The first group, as indicated by blue, means that these are the active contributors. So these are the people that are still part of a team, they're still contributing to that code base. Then you see that there are different shades of gray. So this is code written by former contributors. So these are people that have already left our organization, right? They're working somewhere else or on something else. So this is so the gray shades identifies the parts of the code which simply might lack detailed knowledge of the solution. But what's so fascinating is that we can now simulate the impact if one of those core contributors leaves. So I picked one of the people at the head of the curve, and I simply looked at in which parts of the code is that person the main contributor. And I marked those parts using red, and you see it to the right on my screen now. So if that person leaves, all those parts indicated as red are parts where we're going to lose the main contributor. Should I be worried if I am the manager of this team? Yes, most likely. So how do I act upon this data? Well, what I tend to do is that I look for 3 different factors here, because as you saw, there's so much code where we would potentially lose the knowledge, and we cannot act at all of it at once. So I want to make it actionable. So what I do is I combine 3 different factors. First of all, I know that if the main contributor behind a piece of code leaves, that's a risk in itself. The impact is larger if it's in a hotspot, because that means the code is relevant. It's very likely that we will continue to work on it. And 3, it's a real issue if that hotspot also has a high complexity and low code health, because then it's going to be extremely challenging for another developer to pick up that work. So what would I do? Well, once I have kind of narrowed down the data to those few parts that tick all these 3 boxes, what I would do is I would make sure to onboard a new developer. Maybe I would even make sure to pair up the developer who's going to leave with the developer who's going to be part of a team, and have them refactor one of those hotspots together so that we can mitigate an upcoming knowledge risk. So there are practical uses for this, but the main reason I'm showing you this data and these examples is because I really want to point out that there's so much more to code complexity than the code itself. In particular, social factors are going to influence how we perceive a code base. And those social factors are things like system mastery. How well does the current team know the code base? And in particular, we tend to overestimate the complexity of unfamiliar code. And on the other side, we might also underestimate the complexity of code that we know well, meaning that others will have a hard time to get on board in that part because we keep so much of that complexity in our head. So my advice is to get objective data on the code base. It really, really helps to identify the weak and the strong parts of the solution. Now, I hope I've inspired you to try this out on your own code. And to get started, we need some tooling. And let me tell you that behavioral code analysis is a pretty new discipline. In fact, when I started to work with these techniques, like maybe 10 years ago, there weren't any tools available that could do the kind of analysis I wanted to do. So I started to write my own tools. And I open sourced my first tool suite. It's called CodeMath, and it's available at my GitHub page. It's completely free and open source, so you can just download it and get started. And CodeMath is a command line tool. So this might be like a simple first steps towards calculating hotspots and all that stuff, which CodeMath can do. Since I wrote CodeMath, I've been spending my past 5 years working on something that I call CodeScene. And CodeScene is the evolution of the behavioral code analysis in IDs. So what CodeScene does is basically it automates all those steps, adds the visualizations automatically, and calculate things like code health automatically. So CodeScene is available as a community edition. That's entirely, the community edition is entirely free. So if you enjoy these IDs, please have a look at CodeScene and consider to support it. Finally, I also want to mention one more option that I find really interesting for quick experiments, and that is the Git client itself. So there are so many things you can do just from the command line. And my book is full with examples on that, but I want to show you my favorite example. Did you know that you can specify git log with the -l flag? And if you do that, then you can specify a function inside a file, and you can have git trace the evolution of that function. So this is basically like a simple X-ray directly from the command line. Isn't that cool? Now, those are the tools. I'm going to give you some more references, but before I do that, I would like to wrap this up by taking a step back and looking at what does a behavioral code analysis actually do for you. And I think it's important to point out that the techniques I've been showing you today, they don't replace anything, save maybe speculations and guesses, but they don't really replace anything else that you're doing today. Rather, I view behavioral code analysis as a complement to your experience and your expertise. Because software development at scale is a challenge, and I'm pretty convinced that we need all the support we can get so that we can focus our attention and precious time to where it's likely to make the biggest difference. And I hope that this session has inspired you to investigate the field in more depth, because I've really just scratched the surface of what's possible. And if you want to read more on this, I blog regularly at codesyn.com and occasionally at adamtornhill.com. If you want to read more on hotspots and read about other analysis techniques together with different examples, then please have a look at Software Design X-rays, which is full of behavioral code analysis techniques to address technical debt. And finally, if you want to have a look at some real-world code bases, please have a look at codesyn.io, where there's a showcase page where I have prepared a bunch of analysis interactive so you can explore hotspots yourself in a bunch of well-known open source systems like React and Docker. So with that said, I want to make sure we have plenty of time for questions. And before I take questions, I want to take this opportunity and say thanks a lot for listening to me, and may the code be with you. Thank you.
Thank you so much. That was great. I love the hotspot pictures. That makes it so clear to understand what's going on in the code base. I'm going to take some questions and relay them to Adam. I'll first look at Zoom chat, since that's going to disappear at the end of the session, and then I'll take a look at Slack. And just a reminder, we are in room-B in the Slack channel. Okay. So one of the first question, when you trend complexity over time, what's the measure? Since you pointed out the best way to measure is with multiple separate metrics.
Yes, that's correct. So the thing is, I'm using multiple different metrics. And what I actually started out with was that I just counted the number of lines of code in each revision. And it's very primitive. But the thing is, if you look at the research, you will see that the number of lines of code is actually a decent approximation of the code complexity, in particular if it goes up, because trends are always actionable. So if you don't have anything else accessible, that's the simplest way to start. Then I added this red line, the complexity dimension. And what I do there is that I started out by just counting the number of indentations in the source code file. And again, it sounds absolutely crazy. How can such a thing possibly work? The reason it works is because there's some pretty good research that again have studied a simple metric like indentation-based complexity and compared it to more elaborate metrics like cyclomatic complexity, and found out that indentation-based complexity performs just as well, because we never ever indent our code just at random, right? So the indentations carry meaning. So that's what I use. And what I've started to work on recently, which is much more complex, is that I parse the code, I analyze the code for different code smells, the different code health aspects, and then I kind of aggregate them together at each point in time so I can get the trend in the aggregated code health. So there are several different levels you can do this at, depending on how involved you want to be.
Thank you.
Hope I managed to answer the question.
If there's a follow-up, I'll keep an eye out for it. There are often issues that are larger than a specific module or function. How do you identify or handle system level or architecture tech debt?
That's a really interesting question. I covered that in the second part of software design X-rays. So there are basically two different things I do. First of all, you're absolutely correct that in many systems there are, the architectural level, it's simply the best entry point to any analysis because the system is so large. So what I do is I simply aggregate the metrics from the different files into architectural components. So I create like a simple specification that tells my analysis tools that, hey, everything located under this particular folder, treat that as the architectural component framework, for example, right? So aggregate the contributions to that, meaning that I can get the hotspot at an architectural level. So then I know where to focus first. Then there's a very different behavioral code analysis technique that I didn't cover today, but it's one of my favorite techniques. It's something called change coupling. And change coupling is fascinating because it's something you can only calculate from version control data. It's just invisible in the code. And change coupling is about the things that tend to change as part of the same change sets, the same ticket, or the same commit. So if you find that these two different architectural components, each time you modify one of them, you have a predictable change in the other one as well, then you kind of know the logical dependencies between them. And that combined with hotspots can usually give you a very good idea of the system level complexity. So I hope I managed to answer that question.
Thank you. And I'm moving into Slack now. So if anyone sends more questions to Slack or Zoom, I'll keep an eye on it. When you say there are no measurements of complexity, and this question came before the cyclomatic complexity, but there's another part of it that I'm going to keep asking. What's your thought on using cyclomatic complexity and tooling like Code Climate?
So I'm obviously a little bit biased there, but I'm going to do my best to answer. So I think that static analysis tools, so I said that I don't view behavioral code analysis as a replacement for anything. It's rather a complement. So I find that static analysis tools are useful as a low-level feedback loop when writing code. I'm using static analysis myself, like different linters and stuff like that. So the advantage of static analysis is that it can capture certain mistakes and stuff like that, right? So there is definitely a value to it. That said, when it comes to technical depth, static analysis doesn't really have much to offer because static analysis tools, they don't consider the temporal dimension, right? The time dimension of code, which we need to prioritize technical depth. And that is by design because that was never within the scope of a static analysis. So most of the problems I've seen with static analysis is when people misuse the techniques for something they weren't intended for. So that's my take on it. I'm a fan of static analysis, but I think it's best used as a low-level feedback loop during development. And then we need another set of techniques to actually identify and prioritize tech depth.
Thank you.
Hope I managed to clarify that.
Thank you for the additional information. We often identify our tech debt as we work. Things like cutting corners or adding another JIRA issue to the backlog. How does pre-identified tech debt stack up against the tech debt identified by analysis?
Yeah, so that's interesting. So there are things that the behavioral analysis cannot catch. So for example, you might run with the outdated library. So you might run an old version of your programming language. And a behavioral code analysis doesn't focus us on that. So that kind of, and you can argue that outdated libraries and things like that are also technical debt because we decided to cut corners by not upgrading, right? But those tend to be the things that have visibility, that are easy to identify. What I tend to see is that I have so much data on this that once you have a complex hotspot and then you look at the trends, you see that file, that module has usually been a problem for years. And some of the hotspots, they are kind of like, I don't know if you use that expression in English, but they are like boiling a frog, right? So, complexity tends to be there from the beginning, but then it just grows and grows and grows. And it's not really clear that this is happening, right? So I think the main contribution of behavioral code analysis is that you now have a set of metrics that are pretty easy to explain to non-technical stakeholders like product owners and business managers. I do that all the time. And those kind of people, they tend to appreciate it because they can now suddenly peek into our otherwise inaccessible world of code, into that black box that is IT to them. And we can now have a conversation around some real data. And we can now make those trade-offs that, yeah, we cannot continue like this. We really need to take a step back and invest in improvements. So it kind of tends to help with finding the right balance between new features and the improvements. So I hope I managed to answer that question. I know I answered something.
Thank you. How common of a practice is this hotspot analysis in industry? Do you think there is an opportunity for more formal tooling to be built to perform this analysis?
So it's not mainstream, but it's getting there. So I've been working more or less full time with behavioral code analysis over the past 5 years. And I noticed that the technical debt has gotten higher and higher at the agenda in many organizations. And I understand why, because it is a problem. It simply takes away so much of our time. And that's time we could have spent on something else. So if I'm talking about CodeSyn, I think we have roughly 14,000 users signed up and that are analyzing different code bases. So it's, you know, I wouldn't claim it's mainstream, but it's getting there and it's growing rapidly in popularity. And yeah, I'm doing my best to promote it because I actually started out with these techniques to do my own job a little bit easier.
Thanks. Is there any relation between test coverage and the evaluation of complexity?
Oh, that's a beautiful question. I like that because actually I have to tell you this. What we did last month on CodeSyn was that we released a new feature. We released like a plugin system. And one of the first plugins we did was for test coverage so that you can kind of, when you find those hotspots, you can immediately see the coverage of that module. And the idea was simply that it's an important piece of, I'm not the biggest fan of code coverage, right? But it still carries some information. In particular, if I want to refactor a hotspot and I know that it has a good coverage, then I can most likely do that in a safer way. If it doesn't have coverage, I might have to start by writing a safety net. That said, what I tend to find is that, yeah, if you have test coverage, that's already a good sign. But what I tend to see is that some of the worst technical debt that I've ever seen tends to be in the automated test code. And I think the reason is because we as developers, we tend to make a mental divide between application code that we know is important, it's vital that we keep it clean and easy to evolve and all that stuff. And then we have the test code where quite often we're happy if we get around to write any of it at all. So I think that part of the explanation. The other part is I think that automated tests it's mainstream now, but it's a relatively new practice. It's been mainstream for maybe 10 years, 10, 15 years. Right? So I think that we as a community, we're still learning what good test automation actually looks like. And I think that we're not there yet.
Thank you. And I don't see any further questions in chat, though if there are questions later on, we have the Slack channel room B where people can ask and hopefully get those questions answered. So we're going to wrap up here. Thank you very much, Adam. I love that talk. And I hope that I can try to use this data in the future.